Hello, guys. Good afternoon to everybody. Waiting for the last people to take their seat. Really, it's a big pleasure for me to welcoming you at Cisco Live. My name is Alberto Donzelli. I'm a solution engineer working in the global specialist organization, focusing on routing architecture. And with me today, I have a couple of colleagues from that are testimonial of an important customer of ours. It is the Ministry of the Infrastructure in the Netherlands. They are local here, and they will share with us their experience with segment routing and segment routing v6. The session is going to cover quite a lot of topics. It wants to be an overall introduction of segment routing, both segment routing MPLS and the ServiceX, to give you a flavor of what the technology can allow and to give you a flavor of all the benefit and application that you can get from the end-to-end, starting from the network itself and going also to explore what we are expecting to see in the future, also in the data center and in the cloud. So why we need something different than what we have today? Essentially because network has not changed in the way they are organized and deployed for the last 20 or 30 years. So we have IP, we have MPLS on top of it, but there has not been significant change and innovation in this space. Networks are still too complicated to be automated, and we want really to move to a network that will be much better automated, self-healing, and capable to carry service not only best effort services, but also service with SLA. In the technology era that we are in, AI is coming as a buzzword everywhere. We are expecting to have a much better and reliable infrastructure, capable to cope not only with best effort services, but also with highly guaranteed services, bandwidth guaranteed, or delay guaranteed services. And segment routing is promising to make this network easy or easier to deploy and maintain. What are the challenges of the existing network? Essentially, existing network were, particularly the big networks, were built in a different domain, starting with access aggregation, then core and data center is every of this domain was really deployed as a standalone domain. And in many cases, you need to have interconnection function in between domain. This can be simplest border router or can also be real UNI between one domain and the other with all the need to do a configuration and stitching of services end-to-end. So the result of this is that everything is very difficult to deploy. The services is fragmented across multiple domains. To deploy the end-to-end services, we need to touch many points in the network, and this is becoming also difficult when you have to decide where to place the service delivery point in your network itself. So where we want to go with segment routing is essentially enable something that we call a segment routing fabric. Is an IP fabric that is going to be in a condition to have a stateless fabric across multiple domains. Oh. Sorry for the feedback. If I look there, it's going to come with a feedback. So we want to deploy a stateless fabric, and this. Let's try to position here. The stateless fabric will enable to have an end-to-end service, only touching the endpoint of the service itself and not having to configure multiple points inside the network itself. This will enable you to have end-to-end service assurance spanned across multiple domains, have a full automation to be significantly improving what is the work needed to deploy, maintain, and configure the services, and overall achieve a much optimized infrastructure, lowering overall also the cost of the infrastructure itself. The network that you want to build, enabled with segment routing, is a network that can span multiple domains, is a network that has a standardized way to deliver services based on multi-protocol BGP, either layer 3 VPN or EVPN, is something that enables network slicing, meaning that not only you want connectivity, but you want connectivity with this SLA. And you can define that a service has to run on top of a low latency path, on top of a secure MACsec enabled path, and not only on a best effort path end to end. And in the end, we want to have a network that is easy to automate, because the complex is the network, the more complex is automation. And we have seen in the last 10 years that the complex network are very, very difficult to be automated. And this is very well recognized by the market itself, right? So there is a lot of talking today about autonomous networking. An autonomous network, ideally, is something that is self-maintained and self-reconfiguring in case of problems. ETSI has said that the first thing that you need to do if you want to achieve this goal is to simplify the current way that the network are deployed, because the way the network are deployed today is too complex, and automation cannot really overcome the complexity of the underlying layer itself. Sorry. So what is now segment routing? With segment routing, we have changed the way the network is programmed. And we have changed the way, because IP networks are usually networks that are routing traffic based on hop-by-hop behavior. So the router has been for 30 years a network devices that were routing having visibility only on the next stop routing. With segment routing, we want to enable the IGP, so the routing protocol, to be in a condition not only to send packet across the network accordingly to the shortest path, but eventually to do traffic engineering starting from a source routing paradigm, meaning that it is the source that decides the path, and the path is encoded on top of the packet itself. The other thing that we want to do is not to use any additional protocol to program this path. Since every router will have all the basic knowledge to compute the path, it is the IGP itself that can do the computing of the path itself. For example, MPLS will not need any more LDP to program the path, because it is the IGP itself, OSPF or ISS, that is going to program the MPLS label. We are releasing this with MPLS and IPv6 data plane, so we will have two options to install and deploy segment routing. And again, you can operate everything here without any additional protocol like we used to have in the past, RSVPT or BGP-LU or LDP. In terms of protocol, we want to achieve a massive simplification. So because with this kind of optimization, we move from a stack of protocol that has been created over the last 20 years to cope with all the application that we need, and we could replace it with extension to existing routing protocol. And again, it is possible to have a data plane that is working on MPLS or a data plane that is working on SRv6. so IPv6 directly can be used for the segment routing data plane. What is very important in everything is related to routing and IP routing in particular is standardization at the base of interoperability. We have more than 70 between RFC and draft released. Here I have listed the major ones that are related to SRMPLS and SRv6. The one above is a unique definition of the segment routing architecture that apply to both data planes. And then there are specific RFC that are related to the additional functionality and TLVs that we have enabled on the existing protocol. So no new protocol has been created. Everything is additional to existing protocol, and the addition has been designed to be fully compatible with the past, with the existing infrastructure. So let's now go a little bit into the basic block of segment routing, dig a little bit more into what segment routing it is. So essentially, if you want to go from a source to destination, you want to set up a segment that is a forwarding instruction that is driving your packet to the destination. If the forwarding instruction is to drive the packet over the shortest path, you will have one single segment. You need only one single segment, is one label that is coupled to the destination, and that will bring traffic to the destination. If you want to have a path that is a traffic engineering path, instead of putting one segment that is the destination segment, you can put multiple segments on top of the packet itself. So it is the packet that is bringing the path with itself when it's going and flowing into the network. This means essentially that the network and the routers are not only capable of doing next-stop routing, but have the possibility also to decide to have different path and traffic engineering path into the network. It is for SR MPLS, the segment is represented by a label. For SRv6, the segment is represented by an IPv6 address. Two are fully compatible, one with the existing infrastructure, so you can deploy SRMPLS in parallel with the existing LDP infrastructure, and you can deploy also SRv6 in parallel with the existing MPLS infrastructure as an overlay, as ships in the night. You deploy dual stack in your network, and you can enable this new routing paradigm. When we talk about segment, there are many possibility or segment flavors, but they are divided in two categories. One that is a global segment category. The global segment category is essentially representing a segment that is unique in the network itself, so has the same semantic meaning all over your network. So it is a forwarding instruction that is installed in every router with the same value and with the same intent for the routing forwarding. A local segment is known everywhere in the network, but is only installed and programmed locally to the node that is essentially assigning this local segment itself. To make the example more clear, let's see the most important segment that we have that are the IGP segment. There are two segments. One is called prefix segment or node segment. These two can be seen as synonyms. And the other is the adjacency segment. One, we will see it is a global prefix, and the other, it is a local type of segment. So suppose that when you configure on the router his IP address, his loopback address, in addition to that, you can configure also the label that is assigned to that node. So if you do like that and you configure the loopback and you configure the label that is associated with that loopback, you automatically can distribute this information using the extension of ISIS or OSPF. So all the nodes will receive the binding of the address, of the IP address and the label without needing any any LDP to distribute the label protocol itself. So we have already achieved one big optimization. I can get rid of LDP and distribute all the label all together. Every node will receive that the prefix 1116 is bound to the label 16006, and they will install an entry in the table, in the routing table, and the entry in the routing table will point to the shortest path to the destination. This also implies that if you have an ECMP path, you will have a load balancing of the traffic over the ECMP path. So this entry will be the same for every router in the network. So router number 2 doesn't have any ECMP path to the destination, but the same forwarding entry, 16006, means shortest path to 1116. And the same, you arrive to router 4 that has the same entry again, achieved very simply without any LDP. You distribute the label and you have your equivalent to LDP information on the network itself. The other category, and this is an example of a local segment, is the adjacency segment. The adjacency segment is essentially a local instruction that is automatically assigned by the node itself. So every node will instantiate one adjacency for every IGP adjacency they have. So in this case, the node number 5 has 3 adjacency. It will assign 3 different labels to the specific adjacency itself. And it is a forwarding instruction that can instruct node number 5 to route traffic over a very specific link. Why this is very important? Because so now every router in the network has the possibility to encode any path in the network. So let's just suppose that here we have a link that is 1000 in a metric. So this link will never be used by the IGP default path itself because nobody will use it normally, right? So, but suppose that I want to instantiate a path that is going over that specific link. So node number 1 could encode over a packet the segment that are sending traffic to node number 5 and sending traffic then over the link 10. We know this instruction because we have seen before, right? So the instruction is 16005 to go to node number 5, and then number 5 can execute the other instruction that is the label that is moving traffic over the link between 5 and 4. And so the packet can then be encoded in 1 to be a stack of label. The stack of label is processed over the path, and the path is proceeding to the destination. We have seen these 2 prefix seed and adjacency seed. The prefix seed is also called node seed in many cases. There are other segment type that we can list. We have the Anycast seed. Essentially is a segment that is associated to a Anycast address, so the same IP address announced by 2 different by two different routers itself. We have the BGP prefix seed. So instead of having the IGP to program the labels, you can also have BGP itself to program the label. Imagine for a data center where you don't have the IGP actually deployed only BGP. We have also a BGP peering seed that we can use to do traffic engineering over egress peering engineering links, so over links that are inter-IS links or things like that. And we have another very important binding seed is a instruction that is forwarding traffic over a traffic engineering policy, over a traffic engineering path specifically. And we will go over it when we talk about traffic engineering. And then finally, we have a tree seed. The tree seed is a point-to-multipoint traffic engineering path that can be used for multicast replication, and this is the way segment routing can achieve multicast transport with this technology and without using any additional protocol. So now let's go and look why it's so important that the IGP has all these instructions available from and can make any encoding of a path in the network. So the case of path protection is one of the primary cases that we are solving with this solution. It was not solvable in any other way. So apart from very complex traffic engineering protection. So suppose now that we have our path, we have seen we have 60,006 is encoded in every router. So 1, for example, would go that way. 3 would go that way to go over my network to the destination 6. But then let's assume that you have a failure. So if you have a failure, in principle, you would have to wait for 1 second for having your IGP reconverging and finally be in a condition to send traffic to 1, 3, 5, 4, and 6, right? So why you cannot send the traffic over 3? Because if I send traffic over 3 before the reconvergence of the IGP, I will create a loop there, right? So I will create a loop and my traffic will continue being dropped between 1 and 3. But now, with segment routing, we have all the segment and instruction that would be needed really to send my traffic over a specific traffic engineering path. So the IGP can compute the primary path, and the primary path is configured as 16,006, but it can also compute the backup path using my segment that I have identified before. So for every entry that you have in the FIB and in the network, you can have programmed at the same time active and backup path. And these paths are programmed waiting for a failure, and if a failure is happening in less than a few milliseconds, you can switch your traffic over the backup path. So this is giving a kind of superpower to the IGP to not be only in a condition to establish your active path, but also to establish the backup path for every destination, and happening this for every possible topology in the network. If you have a path, a backup path can be programmed by the IGP itself. To make clear what is the timeline of the ILFA. So first of all, suppose that you switch on your router. If you switch on your router, first of all, your router will do shortest path first for every destination, will get all the reachability, and in almost 1 second or less, depending on the size of the network, it will compute all the path, active path, and then after they finish the active path, they will compute all the backup path. So these two paths will be already programmed in the FIB, ready to go. Only one is active, the other will be backup. So now the network is running smoothly for 1 hour, 2 hours, 10 minutes, whatever, and then something happened in the network. So when something happened in the network, first thing you need to identify that there has been a failure. So if the network connection is directly connected via dark fiber, this is probably taking 1 to 2 milliseconds only. If the network is over a third-party network, it may make use of BFD and take 20 milliseconds, 30 milliseconds, dependent. But once you have recognized that the network, the interface is down, the local node can invalidate the active path, the one that has failed, and in less than 2 milliseconds program the protected path. The protected path will stay in place for another 1 second that the IGP is using for recomputing the path, and then the post-convergence path is installed by the router based on the IGP reconvergence. Note that for the way TI-LFA is working and segment routing is working, the post-convergence path is essentially equal in most of the cases to the programmed backup path. So the traffic is actually not changing path from active to standby. So the net result is that you will have a network that for every entry and every destination will have an active and protected path that can be used to protect in less than 50 milliseconds, but normally less than 10 milliseconds in case of failure. And the overall result is that if your network is designed for two-way redundancy, you will always have 100% of protection in your network. TI-LFA is working for link protection, is working for node protection, for link and SRLG, for local SRLG protection, for local SRLG and node, and also is working for remote SRLG protection. So even if you have a link that belongs to the same SRLG of the link that is failing, and it is not the direct connected link, this will be taken in consideration. Right. So now, what additional functionality can segment routing provide on top of the protection? So now, let's imagine that instead of having only one label to be assigned to my prefix destination, I want to assign a second label. The first label is optimized for the IGP metric, but the second label can be, for example, optimized for delay metric. So with an additional extension to the IGP that is called flexible algorithm, we can realize and define not a virtual topology that can optimize the shortest path, not only based on IGP, but essentially based on any metric. Particularly, one of the most common use cases is delay metric. So you will have this type of capability, fully maintained, programmed by the IGP itself without needing any, again, additional protocol or additional traffic engineering to establish this connection. But to make things simple, because it's also all about simplicity, for delay, we are also enabling the possibility to switch on link delay measurement on the router. So you switch on performance measurement on the router, and the router starts measuring with a precision of microsecond the delay between two routers, so essentially the delay of the link, without taking into consideration any buffer, anything. It is really the propagation delay of the router. And this information can be automatically distributed by the IGP inside the topology itself. So the ISIS or SPF topology will have not only the IGP metric, but also the delay metric, and can make optimization based on both of them. But why so-called flexible algorithm? Because it is not only that you can define a virtual topology based on different metric, but you can define topology also based on link affinity, for example, or based on a certain node to be excluded by the virtual topology. Suppose that you want to have a pan-European backbone, so you have an international backbone, but you want to define a topology that is only European without anything is outside Europe. So you can define this topology by having one node not belonging or not belonging to the flexible topology. Or you can define a topology that is based on MACsec link. You color with affinity your MACsec link, and you define that your topology is MACsec only. So this is giving you an incredible possibility to define a complex routing to be maintained directly by the IGP itself. And so essentially you will have that the IGP will maintain this segment autonomously. So if there is a change in the topology, this will be handled directly by the IGP itself. If you have something that can be very complex from a traffic engineering perspective, but you can only use one segment instead of using multiple stack of segments, one on top of the other, to have the encoded path. And finally, you have that TI-LFA can work per flexible algorithm. So you can have also the protected path belonging to the same subtopology. So suppose that you have realized a topology only European, but for protection, you are going to route over Russia. So this probably is something that you don't want to do. So it is important that the flexible topology is working in every condition, also in case of protection. So these new capabilities and infrastructure, the fact that we don't need RSVPTE for instantiate path that are, sorry, I'm looking at the timer that has not started correctly, but anyhow. So these new capabilities imply that we need to redefine the traffic engineering architecture and the way we are organizing and configuring traffic engineering on the router. So first of all, RSVPTE used to have tunnels. It is something we are very used and we have been very used in the past, but here we are not talking anymore about tunnels because you don't have any programmed path inside the network itself. So we are calling it SR policy. The SR policy essentially is the configuration of the source routing node, the ingress node, to route traffic over a traffic engineering path. The SR policy architecture is going to take in consideration both explicit path or dynamic path. The explicit path will be computed, will be not computed, will be explicitly configured by CLI. The dynamic path is essentially computed based on some constraint. Suppose that you want to say low delay, and this is the constraint. The node itself or a controller can instantiate the path. How the policy is instantiated can be local configuration, can be controller initiated, and we'll see that there is another interesting category that is that the policy, the segment routing policy, is automatically triggered by a service, by a VPN service, EVPN or layer 3 VPN. And this is something very beautiful of segment routing technology. So path, again, can be dynamic path, and when are dynamic, can be computed by the head end or can be computed by a centralized controller itself. And when it is a centralized controller that is computing the path, the centralized controller can use PSEP to do the programming, netconf, or any API. In particular, we are envisioning GNMI API for essentially scaling up the capability that the traffic engineering will have, particularly for segment routing version 6. So if you want to go and go in more detail of what a segment routing policy is and how complete it is, so you can see that, so you define a traffic engineering policy, you give a name that is fairly straightforward, and then there is these two numbers that are very important. Is one that is completely new, that is the color. In this case, the color, we will see what it is. And then we have the destination that is common to other technology, traffic engineering, other traffic engineering technology. So, but the mix of color and endpoint is uniquely identifying your traffic engineering policy inside the network. Then we have the binding seed. The binding seed is a label, is a segment, local instruction that can be used by anybody else in the network to stitch traffic inside the policy. So if you send to a node a packet with the binding seed will be replaced by the policy seed list. And so you can essentially make a very effective stitching between policy on one side, the network to the other. Then you see that you have a candidate path, right? So you have multiple candidate paths because in segment routing policy, you don't have to define multiple paths in a different configuration, but you can natively define active and backup path as part of the same configuration of the policy. In this example, we have a path that is essentially dynamically computed based on a specific metric and based on specific affinities. And then this path is computed dynamically by the head end in this case. It could be also computed by an external controller eventually. But also we have a second candidate path that is here with a lower preference. So the higher preference is the preferred path, the active one. Should the first one be unavailable for any reason because it is unvalidated, because you have a link failure in the network, the second path is activated, and then you can have an active backup path configured in the same policy itself. So the other important thing that we have done with segment routing that was almost impossible to do in a granular way with RSVPT is that when you configure explicit traffic engineering, you can configure multiple segment lists. So the same path could have one segment list that is going over a path and the other segment list that is going over the other, and you can specify weight for each of them. The net result is that you can have not only load balancing, but you can have weighted load balancing between the two paths. In this case, we would have 80% of the traffic going in one path and 20% over the other. So we have solved another big issue. So we were saying that color is going to enable some very effective traffic steering over the network, because so essentially if you have traffic engineering without steering is like when you have plumbing, but you don't get water, right? So you need to have a very efficient traffic engineering, and in the past, the way we were doing it with PBTS and all these things was not scaling, very complex, impacting performance, very difficult to maintain. So what we did essentially with the use of color is that the color that we use on the policy itself is going to be matched by another color that is the extended community color accordingly to the RFC 5512 that can be bound to every announced route. So the net result is that suppose that I have two policies instantiated, one that is color blue and the other that is color green. I can have a VPN, for example, connected here with two prefixes. I can announce these two prefixes with different color. When I receive my prefix at the ingress node, depending on the destination, will forward traffic over the specific color that is associated to the route itself. So it is a very performant steering with no impact on performance, line rate, and completely automated. Now, let's think that we don't have a pre-configured policy, and we are receiving the route, and I don't have a pre-configured policy for that specific color 128 installed. What we have done is that the router itself can look at the configuration if there is a template configured and set up the policy accordingly to the template configure. As an example, this template, say color 128 is color 128 means dynamic metric type latency. So this is meaning that it is the headend itself that is instantiated a policy to the destination. So imagine that you have a VPN, 100 by 100 PE, and you don't want to configure a mesh. So this is making the mesh for you automatically, full automatically. And this is only making the mesh between the nodes that have route to be reached. And you don't have to spend time in doing maintenance of this meshing and programming it and setting it up. So if this is not sufficient to have a per destination steering of the traffic, for the same destination, we can also instantiate multiple policy, and we can route traffic based on a classification of the packet. So with the per flow steering, we can also steer for the same destination traffic that is going to green or to blue, for example, depending on the SCP value or source destination value or anything that can be programmed in the router itself. Indeed, we are using other steering mechanism. The other steering mechanism are the classic static route associated to the policy itself, or auto route announce, or we have the preferred path for the layer 2 services, or PBTS is still supported on this. But 90% of our customers are using automated steering and on-demand next stop for 99%, I would say, of the services itself. So for the complex configuration of traffic engineering path, we can think that segment routing, suppose that you want to send a packet over a multi-domain. If we know the labels that we have to encode on the node itself, the traffic could span easily different domain. So suppose this is IGP1, this is IGP2, this is IGP3. You have inter-area routers the traffic could go end-to-end very easily, as opposite to segment routing, to RSVPT. But so it is sufficient to encode the right path, the right label stack that will follow the path, and the packet will go to the destination. But now, who can know the path of a multi-domain? This is a path computation element. We have a path computation element that is designed for operating with the segment routing, can get information from the network from multiple domains using BGP link state, and can be used to program the path end-to-end. So if a node number 1 wants to go to node number 6, can ask to the path computation element for the seed list. The seed list is passed to the node is installing the path. The path computation element is part of our controller architecture, crossword network controller. One of the part of this crossword network controller is the path computation element that can be deployed in a distributed mode, imagine like a router reflector. If you want to scale out to a network of 100,000 nodes, you can deploy multiple pair of these per region. And then if you need to have a centralized path programmed for a particular use case, then the request can go up to the controller itself. The controller can provide additional services like bandwidth optimization services is one example, or disjoint path for different source and destination through the network itself. So we have seen some of the use cases that can be enabled by segment routing. These are very common to segment routing, MPLS, and SRv6. You can have use cases we have seen network availability like TI-LFA or protection, microloop avoidance protection. You can have advanced use cases like bandwidth use cases or like disjoint path that are enabled with the use of an external controller. But also we have all these complex use cases intent-based, so in which a service can be bound via color to a specific path, and the automated steering of this traffic can flow over the network without complex programming and automation. If we want to analyze this from a protocol stack perspective, I think that this is very important because this is bound then to the complexity of the network configuration, the router configuration, but also to the coding and the use of the code inside the router itself. So we are moving from something that was designed with RSVPT LDP on top of the IGP to program MPLS network with something that can act directly with IGP plus the extension without needing any additional protocol on top of that. If we want to go inter-domain, we may want to use still for MPLS some BGP LU for the best effort part for interconnecting multiple domains, but we can use the controller-based architecture that we've seen for having a connection with SLA between inter-domain. And then we are standardizing services using multi-protocol BGP, EVPN, and layer 2 VPN are fundamental here. When we go to SRv6, it is going to be very interesting because we are not only replacing all the RSVPT protocol, but also we are replacing BGP LU. We will see that SRv6 can enable multi-domain end-to-end services across the network, and everything is essentially done only with the SRv6, only working on IPv6 packet itself, without any shim layer, no more MPLS. So if we go and look at what is the architecture implication, you can see that so here you have a router that is using LDP, is a complete parallel protocol to everything else. This is essentially going to be very optimized when you have the IGP programming the label. At least we have a full sync between the IGP and the programming of the label itself. Is a first big simplification. But when we move to SRv6, essentially everything is routing, everything is inside the IP fib, and again, the simplification is massive. Some of our customers are saying 70% less configuration, 70% less code use inside the router itself. So, and how are we doing it? So we took it from the base, trying to renew a protocol that was designed in the 80s that was IPv4, that was not foreseeing any VPN, any traffic engineering, any service chaining, and so on. We develop over time what we can call workarounds, right? So to enable on top of a limited existing protocol all these applications. But now with the SRv6, we have the possibility to do it properly on top of the same IPv6 packet. We have the possibility to embed services, to embed VPN, to do service chaining, everything using only the IPv6 routing protocol. And we have done it essentially not modifying anything on the IPv6 itself. We are using the same header of SRv6, and we are using a capability that is inside SRv6, that is the extension header, already foreseen by the standard. But here we are using a special encoding that is the segment routing encoding that can be triggered by having this segment routing for here specified. This is telling a router that the header that is following, it is a segment routing header, so that it has to execute what is inside the header itself. But then we have done something more, because so the way this was going to work is that on top of we have essentially we are encapsulating IP here. You have IP in IPv6, and then we were putting all our segment inside the extension header. What you can realize that if you have a network, and most of the traffic engineering use cases are across your own network, so you have a lot of redundant information that is reported here, right? So you have almost something that is changing is very minimal, and all the rest is the same information. So we have essentially decided that we could do something even more efficient. So instead of going always inside the extension header, we decided that we could fix a block of operation that is essentially defined as the first 32-bit of the address itself, and only signal as a segment the 16-bit that are actually changing, right? So in the example before. With this, we are able, in what is so-called a SRv6 microseed carrier, up to 6 segments inside the same destination address. So it is not necessary for up to 6 segments to go inside and reading to the extension header itself. This is not more efficient from an MTU perspective, because it reduced the MTU of the packet overall, but is also very efficient in terms of forwarding, because so the forwarding based on this operation is much more friendly for the MPU themselves. So This is known as the SRv6 block. This is essentially the microsegment. C as the same as a node or prefix seed, and everything can be announced as what is so-called locator. That is essentially the IP packet that is bringing traffic to a specific node itself. This locator essentially is advertised as /48. It means that all the information that are coming after the 48 bit, so all this, will be ignored by the network, by almost all the nodes. Only the destination node will take in consideration the bits that are coming later than the 48th bit itself. Everything is going to be forwarding accordingly to the longest prefix match. That is the way IP network is working. So suppose that you want to go from node 1 to node 8 and go inside a specific VRF and move from 1 to 4 to 6 and to 8. This will be simply encoded with a segment list that is going to 004, 006, 008, and finally you have FFF that is the equivalent of the service label. So it is essentially saying look inside a specific VRF at the end. So in terms of operation, you can see that I go to node number 4 as first because /48 is the only thing that is advertised. When I arrive to 4, everything is shifted 16-bit on the left, and traffic in the packet is forwarded with the new header. Again, the /44 48 will bring my traffic to the node number 6. And then finally, I arrive to node number 8, and in node number 8, the VRF is decapsulated. So in one single seat, I will have the possibility to have up to 6 segment service embedded and without having any further extension header or encapsulation. So very simple. Here there is a magic of, I don't know why this is showing something and the other no, but anyhow, look at this here. So when I configure my router, I configure a specific block of operation that is the same for all my router, and then I configure my specific node segment. This information is spread as a IP/48 route to the destination. All the node knows it, and all the nodes can use it. So here you have the possibility to have the forwarding. Suppose that you want to have multiple segments. We have seen that you can address multiple segments, but if the transit node does not have anything to process, all the forwarding will be based on pure classic routing. If the shortest path is not enough and you want to have, for example, FlexAlgo, you can define 2 different blocks of operation. One that is ending with D, that is a block for the FlexAlgo, as an example, low delay, and the one that we had before. So one block will follow the source to destination accordingly to the shortest path, and the other to the delay path. Or I can build a segment based on a computation of a traffic engineering policy, so I can have the same example I was showing before, going from source to destination and passing through a node, a very specific transit node. This is allowing, for sure, ultra-scale, the possibility to have the extension of segment routing not only to a very large network, but also in the future to extend to data center or to the cloud itself. But what is very important that this is pure IP, so I can redistribute route from one domain to the other domain. So it's not like a LDP that is limited to the knowledge of the /32. I can announce route from one domain to the other, simply redistribution of route. I can use summarization of route, so I can enable larger scale and can still have inter-domain connection and connectivity. So to recap a little bit, we have essentially a programming platform for programming the network as a fabric. By using the microSED, I can do everything that is from basic reachability from source to destination to VPN virtualization. This is going to enable TI-LFA for protection and resiliency, traffic engineering, and service chaining if I want to pass my traffic over the service chaining. Since I can go and span multiple domain, we can go from DSP network even to on-premise CPE, managed CPE, suppose, and we have an example later with our customer here that is showing that this is possible, but also extending it to the cloud. And yeah, so here there are some standardized programming function. Are the end function that can be performed by the node itself, are the one that are enabling the node to build any possible services in terms of layer 2 and layer 3 services, layer 2 VPN and layer 3 VPN, per VRF, per CE, everything is possible by using these standardized behaviors. Nothing so preempt you to define your OR function that is executed by a specific node. So every possible application is going to be possible in the end. But there is another very interesting capabilities that is enabled by SRv6, because MPLS has failed to reach the host itself. So reaching the host is something MPLS can never achieve, has not achieved in 20 years. But SRv6 from the beginning was supported in Linux, was supported in hypervisor. It is supported natively by the host itself. And here I want to show you what this could lead. Because so when we talk about data center, and when we specifically talk about data center for telco, but it's also applicable to to large enterprises, what is happening is that if you want to distribute the data center, you need to replicate multiple data center infrastructure at the border of the network. And the data center infrastructure means that you have to deploy a spine and leaf, and more importantly, you have to deploy DCI interconnection function that are essentially dedicated routing function between the domain itself. So this is mainly due to the fact that in today data center VXLAN is the solution that is deployed. So VXLAN need to be replicated, and you need to have a routing between VXLAN via data center interconnection. The need of VXLAN, if we want to go back and make a little bit of story around it, the need of VXLAN is essentially done to replicate in a data center what was the environment normally deployed in a LAN segment inside a specific application where storage and different servers are going to communicate together to deliver the end-to-end service. So the replication of this in the data center required to have the same VXLAN mechanism as a way to program a layer 2 connectivity between the resources that are deployed in the data center. This has been true for the starting of the hypervisor to the NFV infrastructure, where mostly you are deploying virtual machines and you need to interconnect this virtual machine via layer 2 broadcast domain. But the move to the Kubernetes cloud native allows essentially you to build something that is purely routed. Kubernetes likes very much to have only routing between different workers and also between control plane and workers itself. So there is, with Kubernetes and cloud native applications, and with the use of the cloud native, the cloud networking interface, use so-called CNI, to do some optimization in the interconnection of cloud native function to the network itself. So, and particularly with Cilium, that is a cloud native interface that now is part of Cisco, we are fully supporting SRv6. Fully supporting the SRv6 means that your cluster node, your compute, can become a PE of the network itself. So, and by having Cilium CNI programming the eBPF infrastructure of your Linux kernel, you are going to enable a full PE with also the capability of having BGP, both eBGP and multi-protocol BGP, and supporting microSIG. Why it's so powerful? It is really powerful because so suppose that you have in Tekko Cloud particularly your network that is attached to a compute function. And then you want to spin up interconnection between your compute platform and your network. It is sufficient to export the locator via eBGP on one side and on the other, and you have the interdomain connectivity that is enabling your underlay connection between your network and your compute. And then you can have a layer 3 service like a VRF that is going to interconnect your PE function, suppose an antenna, directly to the cloud native Kubernetes container. So the net effect that we will have is that you can define a VPN layer 3 that is actually terminated directly on the host and on the specific pod application of your Kubernetes. Net-net, you could think to deploy compute directly connected to the network, compute platform that has only to distribute the IPv6 information routing via static route or via BGP. This can be deployed whatever you want in the network in a flexible way without having to deploy all this infrastructure, DCI, and so on. And you can get connectivity end-to-end between the cloud-native workers and the destination. This is something where Bell Canada is leading the market. There is, if you are interested in this, there are many presentations available. I leave you here the links that are not only showing that this is possible in the interconnection of the telco cloud, but these are always also possible to extend this type of interconnection also to the cloud, and particularly is working with the AWS by Canada to have the extension directly inside the cloud of the service provider. And with this, I would leave and a pause for me, and I will ask my friend from RWS to come on stage because they can say something about their experience in a SRv6 deployment and the SAR overall.
Thank you, Alberto.
Thank you.
And thank you for inviting us to your session. You have slides? So my name is Michiel Kolen. This is my colleague Kees de Gruyter. We both work for the IT department in Rijkswaterstaat. And Rijkswaterstaat is the executive agency of the Ministry of Infrastructure and Water Management. That makes us responsible for 3 major networks in Holland. One of them is the Dutch water system, the other one the waterways, and the road network. And this includes all the infrastructure such as storm flood barriers, movable bridges, tunnels, waterlocks, and in addition to the waterways and the roads itself, of course. So the 4th network, we from the IT department would like to argue anyways, our IT network. It's a nationwide IT network, one of the largest fiber optical networks in Holland, 5,000 kilometers of optics, based on an MPLS backbone, data centers, and traffic management locations. And the network is really a bridge between an IT network and an OT network for remote operation. It's crucial for data collection, programming, dynamic traffic management, and smart mobility.
Alberto was talking about programmability of the network, and I was thinking, what does it really mean? And on this slide we say it's automatable. I thought it was a new word, but it actually exists. But I wondered that all of you here, most of you, I guess, with network knowledge, understand the difference between an old network and a new network. Old being traditionally MPLS, new means segment routed. In an old network, what you do is you configure a number of machines to communicate with each other, so data goes through it. In the new world, you configure machines statically, and they know what to do with the traffic. And that's a very different way of handling traffic. That's why all the things that Alberto mentioned actually work. That's why you have Flex Algo. You can give it a procedure, and it will read the data in the package and do something with it. So don't look at segment routing as MPLS on steroids, even if you don't use MPLS anymore. It's a completely different way of dealing with a programmable network. That's why on this slide we say deterministic behavior. You push a configuration to a machine, and that configuration is static. Obviously, you can change it every so many microseconds, but it doesn't change because of the traffic that goes through it. It doesn't change because of the protocols that it interacts with. It only knows the sits in the package and does something with it. So it's basically programmable. It's programmable by the data plane and not by the control plane.
So one of the most important aspects of the network itself is convergence. Even if we would have an outage of a second or less, that would already trigger safety protocols for instance, tunnels, and infrastructure would shut down. So even though you can actually recover within a second from that incident, to recover that stateful network of waterways and traffic jams would take several hours. So availability and convergence is an important aspect of it.
Okay, just now is that I expect you all to be from with a network background. How many of you are from a software background? Oh, one. Well, at least I have one person that will understand what a RESTlet API is, a stateless API. In software, when you want to do DevOps, if you want to develop quickly, the key thing that everybody calls out is API. I have APIs, you can use APIs. And then some people say we have REST APIs. Well, the essence of REST APIs is that they're stateless. They have no memory and no need of a memory to actually execute a command. The stateless property is very, very important because that means there's no surprise, there are no side effects. And in case of segment routing, once a package has left the network, all memory is gone. The network is simply the network, it's static. The dynamic route, all the changes, the flex algo, whatever happens is gone once the package is gone. So it's a REST API towards the network, so you can actually apply software, automate the network without any side effects. It's completely deterministic. You know what the network is and there are no surprises. It's your configuration and nothing else. In our case, because of the conversions, if you want to deploy new versions of our software, new versions of our configurations, we can't use side effects. If the network goes down, if it has to reconfigure itself a few seconds, then all the tunnels in Holland might close automatically because of machine safety regulations. So the deterministic nature of segment routing is one of the main reasons why we choose for segment routing already, 4 or 5 years ago. Well, another business reason is that we have some DWDM, like the optical networking. It was nice, it gave path protection, but it's fairly expensive for the size of network we have. Our advantage is we have plenty of fibers, and we don't have a shortage of it. So some of the functions of DWDM really we don't need. With segment routing, you can build something with the same properties as DWDM, maybe not the full capacity of the lines, but we don't need that. But you can build it with IP with only a few protocols.
So that is actually one of the benefits of statelessness, that it's deterministically defined at any point in time. As we mentioned, to recover from a failure in a stateful network, the example that we use here, courtesy of our friends at the Railroad Network, if all your trains are at a different spot where they need to be able to start up your network, you actually have to first recover from that, put all the trains in the right spot, and then you can recover from your failure. The same thing with the waterways. If you have an incident there, for instance, and traffic can be backlogged, you can recover from the incident in seconds. But to be able to push all these ships through harbors, waterlocks, it could actually take hours or even days to recover from that. So that is one of the key drives to be able to have a stateless network, is to be able to recover from incidents really fast.
Well, Michiel took the whole slide for me, so we're making up a little bit of time now. Okay, where are we at the moment? When we started talking with Alberto 4 or 5 years ago about segment routing, SR MPLS already existed. And we implemented it, we did all the tests, and it worked great. But we only use it for the control plane at the moment, because we thought that if you look at segment routing, basically what you want is use the part where you can go all the way to the host, where you can go all the way outside of whatever your MPLS network is. And obviously, SR MPLS doesn't do that. So we use it, our backbone is using it for the control plane traffic, but nothing else. At the moment, we have SRv6 up and running, tested. It's not yet quite in production. We had hoped to get it ready before this, but it always takes a little bit longer. It's up and running, it's fully certified, it's ready to go into production, but we need a little bit of time to roll out the machines. What we use, Alberto called it interdomain, we call it multi-domain, but it's the same thing. One of the issues we have, if you want to go from PPE routers to customer edge, you end up with a security issue. You don't want to advertise all your routes, everything that's in your backbone, towards the customer premises. Well, that was something that actually took a little bit of time, because originally when we talked about segment routing, you had ISIS, and then you talk to a few people that know about networks and say, don't do it, it's too insecure. You can't advertise your whole backbone to, well, in our case, just a cabinet alongside a highway. Well, now there is the multi-domain, the interdomain, and that means that we have basically two domains, which solves many of the security issues. The other thing we have running is actually the replacement of the DWDM. So we have a layer 2 network using Flex Algo to give the same path protection as you have with the optical network. It has the same convergence times. It has a little bit more flexibility because we can actually use all the routes that are in the network rather than the two glass optical routes that we would have with DWDM. It does mean that if we reuse a route because something is broken, that you lose some of the capacity because you get twice the traffic over it. But that's in our case not an issue. So it's more flexible, it's simpler, it's a lot less machinery, a lot less equipment in the data center. So the business case for us is very, very positive.
So as we mentioned already, we have our physical infrastructure, data centers, traffic management control centers, and they are quite easy to protect physically, the buildings anyway. But we also have a lot of our infrastructure in the field or even in the sea. And this is an example in the North Sea. So to be able to physically protect your network infrastructure is not always possible for us, and even if we could, the response time for an incident, for instance, could easily be hours. And this is what Kees already explained. So we had to come up with a mechanism to make sure that we don't display all our assets in an access point to our network.
So in the case of the multi-domain, our PPE backbone is just IS is the standard SFE6. And the white area that goes to the customer premises edge, that's actually signaled by BGP. And the edge routers only get the two nodes that they have to communicate to, nothing else. So it's a very safe way of doing it. The other thing you see, we call it the server hub. For us, a CE is a router, but maybe also a firewall, maybe also some other security devices. And it also opens the possibility to what Alberto says, that you can have segment routing all the way into a Kubernetes cluster. This design actually was about 5 years ago that we started building on it. And we're now at the point that actually with segment routing, we can really make use of it. How are we doing on time, Alberto? There's one more slide, but I think your finishing is probably more important than us talking for the next half hour.
You can go to your slide.
Okay, well, some other, I call it fun stuff, because we reckoned we would run late a little bit. But this is what makes it really nice for the network people. What we have running at the moment, and what will be SFE6 later, is that we have two stacks running, one for IP4 traffic, one for IPv6 traffic. And the nice thing is they actually run within the same MPLS VPN. So we can move over to a new protocol without touching the old configuration that runs what it is. If we switch over, we think it goes without packet loss. We tested it, it goes without packet loss. But if it doesn't, we can switch back and try again. So the migration shouldn't take more than a second. The last one is perhaps a little bit difficult. If you go over the highways in Holland, there are these signs over the road. Those are connected to a ring topology network. So there's fiber optics on one side of the highway and there's fiber on the other side of the highway to close the ring. The problem is you need to dig in fiber optics twice, so it's very expensive. What we do now with the segment routing is actually have fiber optics on one side of the road and close the ring over the backbone over a layer 2 network. So we have the same protection, a little bit better actually, because we're using 2 nodes in the backbone without twice the fiber optics. Now, there are a number of highways in Holland that don't have fiber optics at the moment. So this is a money saver that goes into the millions of euros. It's a very interesting development, and it's. I'm not saying it couldn't be done on another way, but with segment routing, it's easier. Okay, thank you.
This one only. So first of all, Chess and Michael, thank you so much for sharing your experience. This is fantastic for us. I believe that this is showing that segment routing is not only something valuable for service provider, but also public sector, big enterprises, everybody has a routed up, so a wide area network essentially can benefit from this. So now I want to quickly close stating that so segment routing overall has a very large deployment successes across multiple markets, across multiple geographies. It is really going mainstream for most of the customer, for at least for MPLS for sure, but also for SRv6 is getting a lot of traction. So we are seeing during the last year a very big increase of adoption, because in the end it is an overall simplification and the possibility to get really end-to-end with scale very effectively. So the importance of IPv6 and the distinctive value of SRv6 is again that is not going only on the network equipment. It is going on the applications. It is going on the hypervisor, on the host, and this is giving extremely great value to the solution overall. We don't have to forget that everything is standardized, and we had a very good interop testing going on last year. It has been a very extensive tested. It has used for everything the microSeed as a forwarding infrastructure with all the major network vendors participating to it. You can find the link on the presentation if you are interested. And I want to leave you with a consideration. We are building IP to be as best as ever. We are improving IP to come back and be the protocol that can solve all the possible use cases with IPv6, SRv6. We are also, in parallel, building everything is relating to the possibility to measure performance on the IP infrastructure, something we have missed forever, right? So it is the possibility to know where the packet is going in an ECMP network that can have 128 path itself. Why it is so important? Because if you want to build something that can grow to be an autonomous network, you need to have the measure coming from the network itself. We are embedding probes inside the hardware to scale up to 14 million probes per second per MPU on our routers, and we are building a solution that is called integrated performance measurement that will measure all the quality of your interconnection between source and destination in an automated way for all your network, time series to be correlated, having the possibility to inject the machine learning and artificial intelligence to do inference and really tell you exactly if there is a problem in a proactive way, where is the problem, and eventually correct it in an automated way. For doing this, I will strongly suggest to use this session also as a teaser for whatever topic is really interesting to you. You can come at the World of Solution. Everything I was telling you is demonstrated there. You can really touch with hands, but also you can go in more detail on IPv6 SRv6 solution. There is a Jakub session, very detailed, very spot on. He's a fantastic presenter. I would strongly recommend. And also Pablo is having this interesting session that is covering the further enhancement to SRv6 and the IPM solution I was telling you. troubleshooting session and everything else can finish your education. Don't forget to stay connected with the app. If you want to have any clarification, you can use the WebEx space. I will answer to your question. And please fill out the survey. You can have the T-shirt. Finally, a lot is going on also in IPv6 because IPv6 deployment are becoming more and more compelling. So this is a complete roadmap of what you can get in Cisco Live for IPv6. With that, I really want to thank you for your attention. Thank you for being part of this session. I will be available for some minutes if you want to ask any question, and please enjoy your staying at Cisco Live.